the spring installment of this seminar with the talk by David García from University Aix-Marseille, who will tell us about a large deviation principle for empirical measures. So David, please.
Thank you. So first, I would like to thank the organizers for the invitation. It's nice to talk in this webinar. I'm going to tell you about my first work in mathematics. First, I want to motivate a bit. So I will say something about Coulomb gases on manifolds. That's my main motivation. Then the principle, the main results, and then if we have some time, I will discuss about some deterministic version, so no longer random. So everything will be mainly probability. This talk will be about kind of probability. So I will begin by a nice model in the sphere. So we have the sphere as a subset of R3, and we take a function g that is kind of an interaction potential between points on the sphere, defined by this formula here. It's minus the logarithm of the norm between 2 points, and the norm is taken in R3. And we take also sigma. We define sigma as the uniform probability measure on the sphere, and we choose some beta greater than 0. So given this data, we can define what I call a Coulomb gas measure. So it is a measure that is absolutely continuous with respect to sigma to the power of n. So it's a measure on n points, n particles. Here, 1 over c is just a normalization constant because this Pn beta is a probability measure. So we normalize it to be a probability measure, and the main part is this exponential. Is exponential of minus this parameter beta positive times the sum of the interaction between the particles. So we take different points without repetitions. Now, what we know about this Coulomb gas measure is that if we take n points distributed according to this measure, then this happens for any continuous function on the sphere. The empirical mean will go almost surely to the integral of f with respect to sigma. So this almost surely here means that the probability that this happens, or the probability that the empirical mean go to the integral of f, is 1. Now, how can we generalize this for this model? I mean, sorry. We have to notice here that G satisfies this interesting property. If we fix X and we take the Laplacian of G with respect to the other variable, then this is a multiple of sigma, the probability measure, the uniform probability measure on the sphere, minus the Dirac delta at this point X. So this is known in physics as a kind of Gauss law. And what we mean exactly, well, this is in distributional sense. So more precisely or more explicitly, we mean this. If we integrate gxy times the Laplacian of f at y, then we obtain this multiple of, here we have the integral of f with respect to this sigma minus the integral of f with respect to this Dirac delta at x. So this happens for every smooth f. This is exactly what this relation means. And this is the so-called Gauss law in physics. So we may interpret this Gx as the electrostatic potential generated by a point charge at x, this delta at x, and by minus sigma, so this sigma that appears here. So it has a nice interpretation, and we can see that this G depends on what? On the Laplacian, so depends on a notion of metric, a Riemannian metric on the space, and depends on this sigma. So we may have chosen any other background charge, so something different from sigma, and of course any other manifold, so we don't need to speak about the sphere here. So let me do that. Take any compact Riemannian manifold of volume 1. This is just for normalization purposes. And let me call sigma the Riemannian volume measure on M, or the volume measure induced by the Riemannian metric in M, and choose any signed differentiable measure lambda, such that lambda of M is 1. What I mean by differentiable here, I mean that lambda is absolutely continuous with respect to sigma, and its density is differentiable. That's all that I mean. Signed because this density can be positive, negative, whatever, but we need that lambda of M is 1. Given this data, well, given this lambda and this Riemannian manifold, we can define the Green function as a continuous symmetric function such that the same thing that before happens. We haven't put the 2 pi because it's just a constant. So we ask G, for G, we ask this relation to hold. This can be thought now as the potential, the electrostatic potential generated by a charge at x and by minus lambda. So lambda will be some kind of background charge. And given all this data, we can define again the Coulomb gas measure now in M. So we take the same formula as before. We use sigma for the reference probability measure to define the probability Pn, and G is related not to sigma but to this lambda, and this 1/c is some normalization constant. We ask Pn to have total mass 1. Now the question is, what can we say about this Coulomb gas measure? So we can say, one of the things we can say is that if n points are distributed following this Pn for beta positive, and if lambda, we have chosen lambda positive, then the empirical means go to the integral of f with respect to lambda. So it's no longer sigma, but it's lambda, the background charge we have chosen. But if we choose beta equals 0, we can notice the following. We can see that these points, since beta equals 0, the density will be 1, and the points are independent with law sigma. Then by the law of large numbers, the empirical means will go to the integral of f with respect to sigma. So there is a kind of a leap between this lambda and this sigma, and it happens only because we have chosen beta equals 0 or beta positive. So there must be some interpolating regime between these two, lambda and sigma. And there is indeed one. And that's one of the main interesting results for me. For this, we have to change the normalization of beta. We defined, well, in order to not to write sum of g each time, we define hn as the sum of g normalized by n squared. And we redefine the Coulomb gas measure by this formula. So this 1/c is again just a normalization constant. Everything is with respect to sigma to the power of n. And we are taking here the exponential of minus n beta n times hn. So this is somewhat different from before, just a difference in the normalization of beta n. Now, the interpolating regime will appear when beta n goes to some positive and finite beta. And what we will see is that the empirical means, in this case, go to the integral of f with respect to some measure that depends on beta, and that this measure is the solution to this equation. So the measure has a smooth density rho beta. The density is with respect to sigma, and this density satisfies this equation. This is a nice kind of geometric equation that is related to the scalar curvature in the case of two-dimensional manifold, but we will not do this now. The only important aspect of this is that it is the limit, it describes the limit of the empirical means in the interpolating regime. So let me generalize this a bit. So now I can describe the general setting given the motivations I have just described. We take now any Polish space, so it doesn't need to be compact. A Polish space which is by definition separable and completely metrizable topological space. We choose any probability measure on M, and now instead of the sum of G, the sum of the interactions, we will choose directly one function Hn for each n, which is a measurable function from endpoints to this interval. Now, I will define, instead of the Gibbs measure that I defined before, I will prefer to define this non-normalized version because I don't care so much about the 1/c that was here. So it's the same definition as before, except that there is no 1/c. Now we will be interested in the space of probability measures in M endowed with the weak topology. What's the weak topology? With that I mean the smallest topology, such that these functions, the functions that are integration with respect to continuous bounded functions, is continuous. So each of these functions are continuous, and we are thinking about the smallest topology that satisfies this relation, this property. So what can we say, or what we would like to say about this? For instance, using the results from before, we would like to know what happens to endpoints that are distributed according to the normalized Gibbs measure. We want to know what happens to the empirical mean. So find some probability measure nu such that this is true. Or given that we have already defined the topology, we can just see it in this way. So we take 1/n times the sum of the Dirac delta at xi, and we want to know if this goes to nu almost surely. But for this, we need some notion of limit for hn. Hn cannot be anything, because if hn were anything, we shouldn't be able to see what happens at the limit. And the notion of limit is the following. We consider a sequence hn with this property, uniformly bounded from below. That will be important in the theorems. And a limit will be some function h on the space of probability measures on M that satisfies two properties. So this will be called a macroscopic limit if it satisfies two properties. First, for every probability measure on M, the integral of Hn with respect to this probability measure goes to H of that probability measure. And this is kind of the defining property of H. We can recover H by this relation, but we also ask this to hold whenever the empirical measure of some sequence, deterministic sequence of points, go to some mu. The energies of these points, the limit of the energy of these points, bounds the energy of mu. Okay, so this is the only important two properties that will give us some will tell us how the Gibbs measure will behave. So we have this H that is the macroscopic limit of Hn. We have a sequence beta n that converges to some beta positive and finite. And then for every bounded continuous function f in the space of probability measures on M, we have this relation. This is a long relation. This says that the limit of 1/n beta n times the logarithm of the integral of this expression, this is the exponential of minus n beta n, times f, this is the function that we have chosen, evaluated at the empirical measure, and integrating with respect, of course, to the Gibbs non-normalized, this is non-normalized measure. This goes to the minus the infimum of f plus h plus some term. So the infimum is taken over the set of probability measures that are absolutely continuous with respect to sigma. So this seems quite long. Well, this term here is called the relative entropy, and this sum is sometimes called the free energy. So I will define it now. The relative entropy of mu with respect to sigma is defined by this relation, is the integral of the density times the logarithm of the density, if there is a density. And if not, it is just infinite. And we can define the free energy as the sum of H plus 1/beta the entropy. So using this definition, it is easier to state the previous limit. We have this limit is minus the infimum of f plus f beta. Now, what can we say about the normalized Gibbs measure? So this is about the non-normalized Gibbs measure. For the normalized version, we need to divide this by the mass of gamma n. But to understand the mass, we can just take f equals 0. If we take f equals 0 here, this exponential will be 1. So we obtain this. 1 over n beta n times the logarithm of the integral of 1, which is just the mass of m to the power of n. This goes to minus the infimum of f beta. So f here is 0. And using this, we can say something about the normalized version. The normalized version satisfies this limit property. Instead of writing f beta here, we write f beta minus the infimum of f beta. And we have written here this 1 over c that was before, this normalized constant, normalizing constant. Now, this is called a large deviation principle, and I will state it in a somewhat shorter way now. We take endpoints that are distributed according to the normalized version of the Gibbs measure, and we take mu n hat, the random measure that is the empirical measure of these endpoints, under the same conditions as before. And furthermore, we ask f beta to be non-degenerate. F beta has to be finite somewhere. Then we have, for every bounded continuous function f, we have this property. So now we can write expected value instead of integral, and mu n hat instead of this big thing that was a bit of cumbersome, the previous notation. So we have this kind of nice property. And again, this is kind of a Laplace principle. It's kind of related to the Laplace method that we see in analysis. And this will explain or will tell us something about the almost sure convergence of the empirical measure. So why does this tell us something about the almost sure convergence? First, what almost sure convergence this tells us? Well, again, under the same setting, we ask the same two properties, and we ask one more. We ask f beta to have a unique minimizer nu. Then the empirical measures go to nu almost surely. So this is what happens. This is a corollary of the large deviation principle in the previous slide. But why? Why this happens? So this is one of the important things I would like to tell you about, because it's kind of the main motivation at least for me, to study large deviations in this setting. So I will try to describe kind of the proof of this corollary using the large deviation principle. So what is important here? First, there are two properties that are important just to keep in mind. The space of probability measures on M is a metrizable topological space, and f beta satisfies this nice property. These sets, the level sets of f beta, are compact. So they may be empty, but in general they are compact. So what do we need to know? We suppose f beta has a unique minimizer nu. We want to show that almost surely the empirical measures go to nu. This is the same as saying that almost surely for every open neighborhood U of nu, this statement happens only for a finite number of n. So for large n, these empirical measures mu n hat will belong to U. And we recall now the large deviation principle is the following. We define now a C as this infimum. Then the large deviation principle tells us that the limit of this expression is minus C. Or we can also say it this way: the expected value of the exponential of minus n beta n f evaluated at mu n hat behaves like the exponential of minus C times n beta n. So in this way, it seems nicer, kind of nicer to see, I think. Now we are prepared to prove the almost sure convergence. So we take any open set that contains nu. So this is u, this line, kind of red line, is u. Then we take f. We have to choose f properly. So we will take f that is 0 outside u and is positive at nu. So f is a continuous function taking only positive values that satisfies this property. Now, given these conditions, we can see that this constant c is positive. This is because this f beta minus the infimum of f beta is 0 only at nu. So outside nu, this quantity is positive. But at nu, f is positive. So this expression is positive everywhere. And since f beta has compact level sets, then the infimum is attained at some point. So the infimum must be positive. So the important aspect here is that c, this constant c, is positive. And we want to compare what happens, this indicator function. This is one if the empirical measure mu n hat does not belong to u. We want to compare this random variable to this exponential that we know how to understand. So this is the indicator function of u complement. What happens is just this. F is 0 in u complement, so we will have that exponential will be 1 here. And it doesn't matter what happens at u because the indicator function will always be 0 and the exponential will always be positive. So using this relation, we want to understand the expected value of this indicator function. We want to understand the probability that mu n hat does not belong to u. So we take expected values at both sides, and we have this expected value of the indicator is bounded by the expected value of the exponential. But we know that the expected value of the exponential by the large deviation principle behaves like the exponential of minus c n beta n, where c, we have seen, is positive. This means that in particular beta n behaves like beta, so this is summable. The sum of this over n is finite, so the expected value of the sum of the indicators is finite. But if we have a positive function with finite expected value, we can conclude that the sum itself is finite almost surely. And that is exactly what we wanted, because this sum is a sum of 1 and zeros. And for it to be finite, we need that this is 1 just for a finite number of n. So mu n hat does not belong to u only for a finite number of n, of course, almost surely. So for large n mu n hat will be in U. And we have done this for only one U, but we can take a countable neighborhood basis of nu and repeat the argument. Since this is a metric space, the space of probability measures on M is a metric space, we can take this countable neighborhood basis and conclude. So I wanted to show this because it's important for me to say why it's interesting, the Laplace principle. Well, the fact is that I am interested mostly in proving convergences. Now, for our case, the Coulomb gas case, we recall this: G satisfies this property, Hn was defined by the sum normalized, and we want to find the macroscopic limit. So for this, we need to integrate Hn with respect to some measure mu. And we can do this easily because it is just a sum of G. We obtain this expression. And now we take the limit as n goes to infinity. And we can prove that the macroscopic energy, the macroscopic limit of Hn, is this one. So this is just the first property, but the second property can also be proved by using the lower semi-continuity of G. And I will not do that here, but the important thing is that H defined by this is the macroscopic energy, and it kind of makes sense because here we are thinking about n particles and we are taking the energy of n particles, and here we are taking the energy of not n particles but of a charge system, the self energy, let me say, of a charge system. Now we have the macroscopic energy. The free energy will be then the macroscopic energy plus this entropy term. And what happens is that F beta, the free energy, is strictly convex. In fact, both terms separately are strictly convex. And we can take the derivative of F beta in mu and the Laplacian. So the derivative is kind of, at least formally, is kind of immediate to take because this is kind of this is a quadratic function on mu. We can also take the derivative of this with respect to rho. And after taking the Laplacian and using the defining property of G, we can find this relation. So if mu beta is a minimizer of F beta, this has to be 0. And this is exactly the equation we had before. So the reason why this equation holds for the limit, it is just because this is the Laplacian of this derivative, and this mu beta is a minimizer of F beta. So the large deviation principle explains well why we have this almost sure convergence. Now I want to say something about what happens in the other case. This was the first case I described, the case beta infinite. Well, there we have in general to add two more conditions. First, we ask Hn to be confining. This means that if the limit of Hn is finite, the lower limit is finite, then the sequence of empirical measures have a convergent subsequence. So intuitively, this says that if we can control the energy of the endpoints as n goes to infinity, then these points are confined, are in a compact set. Well, more precisely, the empirical measures are in a compact set. And the second condition is this one. We say that H is regular if whenever H of mu is finite, we can find then a sequence mu n that regularize mu in the following sense. Mu n approximates mu, the energy of mu n approximates the energy of mu, and mu n is regular in this sense. The entropy of mu n with respect to sigma is finite. So given these two conditions, we add these two conditions to the previous theorem, and also we ask beta n to go to infinity, and we have the same kind of Laplace principle. So the limit of these are exactly the same integrals, but now the limit it involves not f beta but h. We can think that beta here is infinite, so f beta equals h. And again, this explains the almost sure convergence. We take n points distributed according to the normalized Gibbs measure, and we take the empirical measure mu n hat, so that we have under the same conditions. And we have to ask one more. H has a unique minimizer nu, then the empirical measure will go to nu almost surely. So the proof is the same that I spent 3 slides before. And in the Coulomb gas case, what happens? Well, the energy is this one. And if we take the derivative again, and we take the Laplacian, and we obtain lambda minus mu. So if a minimizer of H should satisfy that lambda minus mu is 0. So the minimizers are lambda. Of course, this does not work if lambda is not positive, because the minimizer has to be a probability measure. So we ask this. In the general case, this is not so easy to understand. This is a bit trickier, but the intuition is always the same. We take the derivative, we take the Laplacian, and we see when this is 0. So this is why we said before that lambda was the limit of the empirical measures in the extreme when beta is infinite. Now, there is a deterministic counterpart of these results that I would like to tell you about now. This is called the gamma convergence. And well, it is equivalent to a gamma convergence. It's not the usual statement, but since it is equivalent, I will state it as a gamma convergence. Suppose that H is the macroscopic limit of Hn, and that Hn is a confining sequence. We have that for every f bounded continuous, again, the limit, now we don't take 1 over n beta n integrals because we are not thinking about probability measures. What we take is the limit of this infimum. So we have the energy Hn plus f of the empirical measures. And we take the infimum over every n points. This limit is the infimum of h plus f. So this gives us, again, an almost sure, well, in this case, it's not almost sure because we are not thinking about random objects, what we take is endpoints that have the minimal energy, so approximate minimal energy. So the energy of these points is near the infimum of Hn as n goes to infinity. And we take the empirical measure mu n hat as this one. So now this is not a random measure, but it is a deterministic measure. And we have, under the same conditions, H, macroscopic limit of Hn, Hn confining, and H with a unique minimizer nu. We have that mu n hat go to nu. Now this is deterministic. This is not almost sure, because again, we are not thinking about random objects. So what's the relation between this deterministic version and the Laplace principle and the probabilistic version? So what happens is that, first, for the deterministic version, this infimum can be rewritten in this form. So instead of taking n points, we take probability measures in mn. We take, instead of hn of n points, we take the integral of hn with respect to this probability measure, and the same for f. So we have this for the deterministic side, while for the probabilistic side, we have this property that is in fact very important for the proof, that minus the expression that we had in the theorem, which is 1 over n beta n, the logarithm of this integral. This is exactly equal to the infimum of the energy plus f integrated, but we have here an extra entropy term. So this is almost the same as the deterministic version, but with an extra entropy term. And we may see now, at least intuitively, how the theorem about the Laplace principle can be proved. This Hn go to H, this F stays in F, and these entropies will go to the entropy from the theorem. So it is in this way, in fact, just with a bit of kind of calculations, that we can prove the Laplace principle. So if you like this kind of results, you can find more information in this work. And I would like to say that the proof is in fact motivated by an article of Dupuis, Lasios, and Ramanan, and that this is also inspired by a book of Dupuis and Ellis. This book uses Laplace principles to prove large deviation principles. So it is a nice book if you like this kind of arguments. And so that's all I wanted to tell you about. I hope you enjoy it, and thank you for your attention.
Thank you, David. So are there any questions for our speaker? Questions, comments?
Actually, I have a question, if it's okay. It was a very nice talk. Thank you very much.
Thank you.
Maybe in this inspiring article, there's an answer to the question, but I was wondering, did you have some other than specific motivational examples of these sequence of these what do you call those, where H is a macroscopic limit of these HNs, where the HNs are confining, and you have a unique measure that maybe occur in the literature, or that they fall under your umbrella of that?
Yeah, in fact, well, the usual motivations in probability are related to random matrices. So we have these random matrix ensembles, and that have this kind of sum of G terms for the energy. But we also have the case of random polynomials that is more involved, and it has an extra energy term, and it can be also treated using this theorem. So it's kind of general, I think.
So that random polynomials. So you know that this large deviation principle of Schiffman and Zeldich for zeros of random polynomials.
Yeah, that's it.
It covers this.
It covers that. Precisely. The case of Gaussian, the Gaussian random polynomials.
Oh, okay. Thank you.
Thank you.
I have a question. So if I understood correctly in the talk, you were defining at some point your H sub n's as sums of green functions evaluated at certain points, right?
Yeah.
Do you have any reason to think that if instead of a green function, it was some other function that somehow made sense? I don't know what other ones, but I mean, are there other functions than green functions that you could do something similar with, and you might get similarly interesting results? Do you know?
In fact, the theorem, if we take any G that satisfies some, well, simple properties, G lower semi-continuous and bounded from below, we can prove everything. So the sum of G satisfies this definition of having the macroscopic limit H. So we can choose any G. Just the green function was for motivation.
Okay. But so all of this theory should still hold if, say, instead of a Green's function, I had something different, like a Reese energy. Yeah,
it works for Reese energies. Well, just what we have to be careful is about this part.
Sure. Yeah, that's fair.
But yeah.
I think for convexity, you may need something like positive definiteness, right? So your free energy is convex.
It is necessary if we want to find, for instance, a limit, but for the large deviation principle itself, we don't need F beta to be convex.
Right, yeah, but I mean, in order to get uniqueness of minimizer thing, like all the good things, obviously, yeah.
Yeah, sure.
So on your last but one page, when you compare the two expressions for deterministic, so that's a nice comparison, right? Because you can see, so the next one, so where you highlight, so you can see that, okay, when this beta n goes to infinity, so temperature goes to 0, right? So you get exactly to deterministic expression. So it makes sense. It makes sense because that's like 0 temperature case.
Yeah. It connects everything.
Yeah, and also in this same. So okay, so I was wondering, maybe this is a silly thing, but it seems the rate n, this n beta n, right? So that's not very important. You could have taken any sequence that goes to infinity, and so basically the point is it doesn't really matter how you approach 0 temperature, does it? So the way n beta n grows defines how you're cooling down.
Yeah, but this is in gamma n also. So it is important because it is in gamma n, in the definition of gamma n. So if we choose different n beta n here, we won't get this this result, this Hn here appears because from the gamma n here.
So the rate actually is important. So this is sensitive to the n factor.
It's important just because we are defining here gamma n as exponential of minus n beta n times Hn.
Yeah, okay, but I guess, okay, so let's make minus, tau of n, where tau of n goes to infinity, and then just replace n beta n with tau of n times beta n. So this would all work, right? Yeah, okay.
Sure.
It's just the same, okay.
I have some technical question probably. In the 2 slides, maybe it was as expected value of exponent of f from mu hat, why it was equal to 1 plus O small of 1.
And this one is the large deviation statement. It is this one. So
okay.
This is exactly the same as this.
Okay. I think.
Yeah, okay, so this is Laplace principle basically, right? So just
that's
the asymptotic, The asymptotic order of e to the minus function is the same as e to the minus minimum.
It is Laplace principle for empirical measures. Yeah,
exactly. Okay, this is great talk. So
thank you.
I guess I'll stop the recording then.